Hello and welcome to this webinar series, Harnessing NISAR, Next Generation Radar Observations for Earth Applications. My name is Erica Podest and I'm a scientist at NASA's Jet Propulsion Laboratory where I study terrestrial ecosystems using SAR. I'm also an instructor with the ARSET program. We're entering a really exciting new era of Earth observation with the launch of NISAR. This mission will provide an unprecedented view of how Earth's surface is changing, enabling routine monitoring of ecosystems, natural hazards, water resources, agriculture, and the cryosphere at a global scale. Although this webinar series is an introduction to NISAR, we will also cover key SAR fundamentals to provide the context needed to understand the mission's capabilities, data products, and potential applications. By the end of this training, you'll have a foundation for understanding how NISAR data can be used to address a wide range of Earth science and decision support challenges. Before I begin, I'd like to provide a bit of background about the ARSET program. NASA's Applied Remote Sensing Training Program, or ARSET, offers free trainings on the use of remote sensing and model data, along with methods and tools for the global science and application communities. Our trainings are tailored to different experience levels, ranging from introductory to intermediate to advanced. ARSET trainings focus on 6 thematic areas: agriculture, disasters, ecological conservation, health and air quality, water resources, and wildland fires. ARSET trainings are either online or in person. All are free of charge and use open source data and software. Some of our trainings are delivered in both English and Spanish, like this one, and all of our training sessions have a Spanish presentation available. Now I'll provide an overview of this webinar series. NISAR marks a new era of Earth observation. A fundamental challenge in Earth observation is monitoring change consistently across the globe, and NISAR was designed to address this challenge by providing frequent, systematic radar observations that are independent of sunlight and that are largely unaffected by cloud cover. So these are the training learning objectives. By the end of this webinar series, participants will be able to identify the characteristics, capabilities, and limitations of NISAR data, recognize how NISAR data can be applied to decision-making related to flooding, earthquakes, and landslides, differentiate between the different types of NISAR data products and their applicability for different use cases, demonstrate how to access NISAR data and tools via the ASF DAC platform to search, visualize, and analyze data, provided case studies related to floods, earthquakes, and landslides. Visualize flooding with GCOV files and generate landslide risk and volcano deformation maps for events of interest using the interferogram, the GUNW files in QGIS. Demonstrate how to access NISAR S-band data via the ISRO Bunity platform and use available tools for basic visualization and analysis. Prerequisites for this training: we suggest the fundamentals of remote sensing as well as an introduction to synthetic aperture radar and its applications. So there was one in 2017 and there was also one in 2024. So both of these contain background or reviews of radar as well as INSAR. We will be focusing on INSAR in this training. The session 3 will discuss INSAR, and as you all probably already know, INSAR is all about the phase of the SAR signal. And this is a training outline. There are 3 sessions associated with this webinar series. Today is session 1, an introduction to NISAR. The next session will be on July 9th, and it will be focused on NISAR data access and tools. That'll be led by the ASF, the Alaska Satellite Facility, DAC, which is the Data Archive Center that holds all of the NISAR data. And then the third session will be on the 16th of July, focusing on monitoring earthquakes, volcanoes, and landslides with NISAR's INSAR capability. And that'll be led by my colleague, Dr. Eric Fielding from JPL. All sessions are at the same time. There is one homework associated with this webinar series, and it will open on the last session, on the day of the last session, on July 16th. The due date for the homework is August 6th. A certificate of completion will be awarded to those participants who attend all live sessions and complete the homework assignment by the due date. Now let's focus on this session, an introduction to NISAR. I will be your instructor for this training. I'm a scientist at NASA's Jet Propulsion Laboratory, where I use microwave remote sensing, particularly SAR, to study wetlands, vegetation growing season in the northern high latitude regions, and land cover and land use change. I also serve as the community engagement and training coordinator for the NISAR mission, and I'm a member of NISAR's science team, supporting the wetlands science area. Through these roles, I help connect the science applications and user communities with NISAR data and capabilities. The objectives for this first session: by the end of this session, participants will be able to identify the characteristics, capabilities, and limitations of NISAR data, recognize how NISAR data can be applied to decision-making related to flooding, earthquakes, and landslides, and identify the different NISAR data products. How to ask questions? To ensure we see your question, please write your question in the Q&A box, which you can locate it by doing a click on the three dots in the bottom right of your of the window in the platform. And there you'll see a Slido, a Q&A option, and you can also see a standalone Slido tab or app. Write your questions or all your questions there, and we will answer them during the Q&A session at the end. And we will try to answer all the questions during the Q&A session. The remaining questions will be answered in the Q&A document, which we will post on the training website about a week after the training. Okay, so let's get started providing an overview of the NISAR mission. So let's start out with why NISAR. Many of the most important changes on Earth occur continuously and often in areas that are either cloudy or under darkness. And these changes occur at either very small scales on the order of centimeters or very large scales on the order of meters. And some of these changes that occur on the Earth's surface are earthquakes and tectonic deformation, glacier and ice sheet motion, landslides, surface subsidence due to groundwater extraction. And there are other changes too, things like forest change and biomass, floods and wetland dynamics. And so to monitor these processes globally, we need a sensor that works day and night and can see through clouds and can measure small to large changes in the Earth's surface. NASA stands for NASA ISRO, which is the Indian Space Research Organization, Synthetic Aperture Radar. It's a joint mission between NASA and ISRO, and it uses SAR to measure and understand changes in Earth's land, ice, water, and vegetation. The origins of NISAR can be traced to CSAT in 1978, which was the first civilian L-band SAR mission in space, and it demonstrated the tremendous potential of radar observations for Earth science and applications. Although the mission operated for only a few months, it transformed our understanding of what SAR could reveal about Earth's surface. In 2007, the National Research Council Decadal Survey identified NISAR as one of the highest priority Earth observation missions needed to advance our understanding of the Earth system through systematic global observations of Earth's changing surface. And building then on decades of scientific and technological advances, discussions between NASA and ISRO began in 2011 to explore a potential partnership. After several years of planning and coordinating, the agencies formalized their collaboration in 2014. And what followed was more than a decade of joint development, integration, testing, and preparation. Those efforts culminated in the successful launch of NISAR from India on July 30th, 2025. And the animation that you see here illustrates the deployment sequence following launch. One of the mission's most impressive engineering features is its 12-meter deployable reflector antenna, which enables the collection of high-quality radar observations over a wide swath. The scientific motivation for NISAR spans multiple disciplines. Its observations support studies of ecosystems and global biomass, ice sheets and sea ice dynamics, natural hazards, agriculture, hydrology, and many other processes that are critical to understanding our changing planet and supporting societal hazards and resilience. NISAR is the result of a highly complex and collaborative partnership between NASA and ISRO, requiring close coordination across all aspects of the mission, from instrument development and spacecraft integration to operations and science. The table here shows the contributions from NASA and from ISRO. NASA provided the L-band SAR system operating at a wavelength of 24 centimeters. The radar system includes a 12-meter deployable reflector, a 9-meter boom, and an approximately 4-meter long octagonal cylinder that houses the L-band and S-band radar electronics. And you saw this in the animation from the previous slide. And the two radar systems, the L and S-band radar systems, can work simultaneously together. ISRO provided the S-band SAR, which operates at a wavelength of 9.4 centimeters, as well as the spacecraft bus and launch vehicle. NASA's Jet Propulsion Laboratory also developed key electronics that enable communication between the spacecraft bus and the radar instruments, along with a high-rate downlink system to transmit the very large volume of science data collected by the mission. The L-band radar alone generates approximately 4.4 terabytes of raw data each day. ISRO provided a separate high-rate downlink system for the S-band radar, meaning the mission operates two dedicated telecommunication systems to support the transmission of this very large volume of data to the ground. The partnership extends beyond the hardware. NASA and ISRO also share mission operations responsibilities and jointly support the science team and user community. Overall, NISAR is one of the most capable Earth-observing radar missions ever developed. The spacecraft has a total mass of 2,700 kilograms and requires about 6.2 kilowatts of power, making it a high-capacity, high-performance system designed to support continuous global observations of the Earth's surface. NISAR has several unique characteristics that distinguish it from other spaceborne SAR missions. First, NISAR carries both an L-band and an S-band radar that can operate simultaneously. And because these radars operate at different wavelengths, so it would be 24 centimeter wavelength at L-band and a 9.4 centimeter wavelength at S-band, this means that they are sensitive. Each sensor is sensitive to different characteristics of the Earth's surface. Another key innovation is NISAR's use of the SweepSAR technology, and this represents a significant advancement over traditional spaceborne SAR systems. SweepSAR enables NISAR to achieve a wide 240-kilometer imaging swath while maintaining high spatial resolution and polarimetric measurement capabilities. NISAR also incorporates highly precise pointing and orbit control, both of which are essential for measuring subtle changes in the Earth's surface through a technique known as interferometric SAR, or INSAR. Pointing control ensures that the radar beam is directed at the correct location on the Earth's surface with the precision required for repeat observations. And orbit control maintains the satellite's flight path so that the same locations can be observed repeatedly from nearly identical viewing geometries. NISAR is capable of repeating its orbit to within 100 meters throughout the orbit, providing the stability needed for accurate surface deformation measurements. Another distinctive feature is NISAR's high observation duty cycle, which refers to the fraction of the orbit during which the radar is actively collecting data. NISAR is designed for systematic global mapping, and the L-band radar operates for approximately 50% of each orbit, while the S-band radar operates for about 10%. This enables NISAR to routinely observe nearly all of Earth's land and ice-covered surfaces. Finally, NISAR is a left-looking radar system. I'll talk a little bit more about this in the upcoming slides, but this means that the viewing geometry provides comprehensive coverage of Antarctica and complements the observations from many existing SAR missions, which are predominantly right-looking. And all of these unique features combined together make NISAR a powerful science and applications tool. NISAR operates at an altitude of 747 kilometers in a near-polar dawn-dusk sun-synchronous orbit. The satellite has a 12-day exact repeat cycle. However, by combining observations from both ascending and descending repeat orbits, the same area can be observed twice within each 12-day period. The ascending pass crosses the equator at approximately 6 a.m. local time, while the descending pass crosses at approximately 6 p.m. Depending on the acquisition mode, NISAR provides spatial resolutions ranging from 3 to 10 meters. And this animation illustrates the acquisition plan for the ascending portion of the orbit. The different colors represent distinct acquisition modes, which are selected based on the characteristics of the target being observed, scientific objectives, and practical resource constraints. For example, sea ice is shown in pink and is imaged using a lower resolution mode because frequent observations are required and the features of interest generally occur at larger spatial scales. In contrast, North America is observed using the highest resolution mode with full polarimetric capability, enabling the most precise measurements. Most of the rest of the world is imaged using a moderate resolution dual polarization mode that balances measurement quality with global coverage requirements. So that provides a little bit of background on NISAR. However, before I start diving into the data and the different science and applications it can address, I want to provide some context about what radar is actually seeing and measuring and what radar is sensitive to. So this next portion will give a brief overview of radar remote sensing. So let's start with the very basics, and this is the electromagnetic spectrum. It's the range of electromagnetic energy that spans from very long wavelengths, such as radio waves, which can be the length of a football field, to very short wavelengths, such as gamma rays, which are the length of an atomic nucleus. Remote sensing sensors are designed to operate at specific regions of the electromagnetic spectrum according to their intended application. Microwave sensors operate within the range delineated in this figure in black, and this range is at a much lower frequency range than optical and infrared sensors. So to put things into context, the wavelength of light is about 390 to 700 nanometers, while for microwaves, it's on the order of 0.3 to 100 centimeters. And because of this huge disparity in wavelengths, the features on the Earth's surface appear differently in the microwave range than in the optical range. And so radar is fundamentally different. The information content is fundamentally different than optical images. So what are the advantages and disadvantages of radar over optical remote sensing? First of all, radar has a nearly all-weather capability. So you can see through clouds and most weather conditions. And I do talk about nearly because if you have very heavy thunderstorms that might affect the signal. It has a day or night capability. So it's an active sensor. We're sending out a signal, and we can therefore acquire images of the Earth's surface, whether it's day or whether it's night. It can penetrate through the vegetation canopy or through a medium. So that signal that we're sending from the sensor can penetrate through vegetation, through soil, through snow. The radar signal has minimal atmospheric effects. And the most important part is that radar is sensitive to two things: structure and moisture, surface moisture. Optical is sensitive to the chemical properties of the surface. So very different information. Disadvantages of radar is that the information content is different than optical. So it's not necessarily intuitive, and sometimes it's difficult to interpret. There's the speckle effect that you've all heard about or know about. That's the kind of the salt and pepper effect in the images. It's not noise, it's actually part of the signal, but it is that graininess in the images that you have to deal with. And then the effects of topography that you need to deal with as well. So let's begin with some basic concepts of radar. It stands for radio detection and ranging, and as the acronym suggests, radar functions as a ranging or distance measuring device. Essentially, a radar sensor emits a signal toward the Earth's surface and measures the time it takes for the signal to return. All imaging radars are side-looking. If a radar were to look straight down, as depicted in the figure on the left, it would not be able to differentiate between 2 points, A and B. In this case, the signal would reach points A and B at the same time and return to the sensor at the same time, which is why you wouldn't be able to differentiate them. However, when the radar is side-looking, as shown in the figure on the right, the time it takes for the signal to reach points A and B differs, allowing for points A and B to be differentiated. Synthetic aperture radars are side-looking systems with an illumination direction usually perpendicular to the flight line. So NISAR is a left-looking radar, and that means it's looking to the left of the satellite's direction of travel. And as a consequence, coverage at high latitudes differs between the Arctic and Antarctic. In the northern hemisphere, the left-looking geometry creates a larger gap around the North Pole, leaving regions north of approximately 77.5 degrees latitude outside the standard imaging swath. And this unobserved area is shown by the red circle in the North Pole coverage map. In contrast, the coverage gap around the South Pole is substantially smaller, as illustrated in the Antarctic map. Let's begin by reviewing how radar images are formed. NISAR measures two fundamental properties of the return radar signal, the amplitude and the phase. So radar pulses travel at the speed of light, and the sensor records only the portion of the transmitted energy that is scattered back toward the antenna. The amplitude represents the strength of the return signal and provides information about the reflective properties of the Earth's surface. The signal power, which is proportional to the square of the amplitude, is calibrated and normalized to produce the radar backscattering coefficient, or sigma naught. And this quantity is a measure of radar backscatter and is typically expressed in decibels using a logarithmic scale. So backscatter values can range from approximately -30 to -25 dB for surfaces that reflect very little energy back to the radar. And these areas appear as dark tones in the radar images. And for example, the one you see here, there's a river that goes through the middle of the image, and that river has low backscatter because the smooth water surface reflects most of the radar energy away from the satellite. In contrast, surfaces that strongly scatter radar energy back to the sensor have higher backscatter values, often exceeding 0 dB. And these areas appear as bright tones in the image and are typically associated with inundated vegetation and urban areas. The second measurement is phase, which describes the position of the radar wave within its cycle at the moment the signal is received. Phase is usually measured in angular units such as degrees or radians and describes, as mentioned, the position of a wave within its waveform cycle. So for NISAR, the radar wavelength is approximately 24 centimeters for L-band and 9.4 centimeters for S-band. And as the radar signal travels from the satellite to the Earth's surface and back, it completes, as you can imagine, millions of wave cycles, and it's just not possible to count all of these cycles. Now, viewed on its own, a phase image often appears noisy and difficult to interpret, such as the example shown in the upper right here. However, one of the most powerful applications of SAR phase is interferometry, or INSAR, interferometric synthetic aperture radar, which measures the phase difference between two radar images acquired at different times or different viewing angles. Now, in the case of NISAR, INSAR, the images are acquired at different times, and that's also known as repeat pass interferometry. And these phase differences between two different images can be converted into extremely precise measurements of surface deformation, often detecting displacements of just millimeters to centimeters. Because NISAR's radar wavelength is relatively short, as mentioned, 24 centimeters for L-band, 9.4 for S-band, even very small changes in the distance between the satellite and the ground produce measurable phase shifts. And this sensitivity enables scientists to monitor subtle surface movements associated with, for example, earthquakes, volcanic activity, groundwater extraction, landslides, infrastructure deformation, and permafrost thaw, to name a few. In addition, the consistency or the coherence of the phase over time provides valuable information about surface stability. So if the phase does not change, that means the surface is stable. And areas with stable phase behavior tend to remain unchanged, while a loss of phase coherence can indicate some sort of change, whether it's vegetation growth, surface disturbance, tectonic movement, or any other dynamic process. So now let's discuss the radar scattering mechanisms. So we discussed amplitude, phase, and NISAR's interferometric capabilities. In session 3 of this training, we will take a deeper dive into NISAR's INSAR data products and explore the different applications they enable. For now, let's focus on how the radar signal interacts with the Earth's surface. So when the radar transmits a signal toward the ground, the way that signal is reflected or scattered depends on the physical properties of the surface. Different types of surfaces produce distinct scattering mechanisms, which are fundamental to interpreting radar imagery, the amplitude imagery. Now, if the surface is very smooth, such as a calm water body or a paved road, most of the radar energy is reflected away from the satellite, much like a mirror reflecting light. And this is known as specular reflection and results in very little energy returning to the sensor. And as a result, these areas typically appear dark in radar images. As surface roughness increases, the radar signal is scattered in many different directions. Some of that energy is scattered back toward the satellite, producing a stronger return signal than, say, a smooth specular surface. And this type of interaction is often referred to as surface scattering. When the radar signal encounters a volume, such as a forest canopy, a snowpack, or even soil, the signal can penetrate into the material up to a certain point and interact with multiple components within it. So in a forest, for example, the radar wave may scatter from leaves, branches, stems, trunks, and the ground surface. And the combined contribution of these many interactions is known as volume scattering. A fourth important mechanism is a scattering mechanism is double bound scattering. And this occurs when the radar signal reflects between two surfaces that are roughly perpendicular to one another before returning to the satellite. So common examples include tree trunks standing in flooded areas or buildings adjacent to a road or flat ground surfaces. In these cases, a large fraction of the radar energy is redirected back toward the sensor. So the smooth surface causes the radar signal to be reflected away from the sensor, but then that perpendicular feature or surface causes that energy to be redirected back toward the sensor, producing a very strong return that appears very bright in the radar imagery. So in the next slide, I'll show you these different backscattering mechanisms, how they appear in a radar amplitude image. So this is an example of the different scattering mechanisms that I just discussed and how they look like in a radar image. So this here, what you're seeing, this is a SMAP radar mosaic of the Amazon basin. It's L-band HH polarization. What I want you to focus on are the different circles, colored circles. So the blue circle is an example of a specular surface. That's the Amazon River. So it's an open water body, and the energy is scattered away from the satellite, which is why it appears very dark. There's a rough surface. That's the red circle. These are areas where there's probably been cut down of trees due to grazing or due to agriculture. So there is some sort of roughness on the ground, and part of the energy is scattered back toward the satellite. So these areas are not as dark as open water bodies, but there's some return to the sensor. And then there's the green circle, that's volume scattering. So the signal is penetrating through the forest canopy, interacting with components within the canopy. And then there's double bounce, that's the purple circle. And in this case, it's inundated vegetation. The signal is penetrating through the canopy. It's hitting the standing water underneath the vegetation. That standing water is a specular reflector. It directs the energy away from the satellite, but then the tree trunks redirect the energy back toward the satellite. So as you can see, the radar can provide valuable information for different things, different science and application areas. It's great for detecting inundated vegetation. It's great for looking at forest degradation, biomass, measures of biomass, looking at areas that have been deforested as well, looking at flooded areas, and looking at, for example, if you have time series, you can look at agricultural growth. So these are some of the things that NISAR can address. Now let's talk about radar and surface parameters as related to NISAR. So let's start with wavelength. That's kind of the most important parameter up front, right? So wavelength is the length of the peak of one wave to the peak of the next wave, or really the position of any point in the wave to the same point in the next wave. In radar remote sensing, we often talk about wavelength rather than frequency. And this is because the length of the wave defines the interaction of the signal with the surface or the medium. And it's therefore easier to associate the capability of the sensor. Wavelength is inversely related to frequency. It is the speed of light divided by frequency. And the higher the frequency, the shorter the wavelength, and vice versa. So the table on the right lists the common wavelength bands in radar. And the letter codes have been arbitrarily assigned, and these were developed for military security during the early stages of radar development. So they're not in alphabetical order. But NISAR operates at L-band, so that's L-band means there's a range of frequencies that define that band. NISAR operates specifically at a specific frequency within that range. That would be 1.257 gigahertz with L-band and 3.2 gigahertz with S-band. There are two important things to remember about wavelength. The first is that the longer the wavelength, the greater the penetration through the medium. That's whatever that is, vegetation, snow, soil. And the figure on the lower left shows that a shorter wavelength, such as X-band in this case, which is around 3 centimeters, will see the top part of a forest, probably the top third or fourth of the canopy, while C-band will penetrate halfway through, and L-band will penetrate all the way through. Now, this is limited by vegetation density, but that's the general idea. So with NISAR that has L-band and S-band, S-band will have less penetration through the canopy than L-band. And the same goes for soil. So the second important thing about wavelength is that the length of the wave will determine the interaction with surface objects. In general, if an object or surface roughness is comparable to the size of the wave, then there will be interaction. The surface will appear rough and there will be energy scattered back. For example, little energy is scattered back from a surface with a height fluctuation on the order of 9 centimeters if L-band is used, and therefore that surface will appear smooth to the radar signal and dark in the radar image. However, that same surface will appear bright to the S-band SAR image because it's on the order of the wavelength, the S-band wavelength, which is 9.4 centimeters. The table on the right shows examples of applications most relevant to specific bands. So if you're interested in forest-type studies and you want deep penetration, L-band is better than S-band. S-band can still be used for forest studies, but it's better for forests that are not as dense. So L-band and P-band are much more suited for, say, tropical forests where you have high biomass, high density. The other radar parameter is polarization, and it refers to the plane of propagation of the electric field of the signal. So irrespective of wavelength, radar signals can be transmitted and or received in different polarizations. The figure illustrates these planes of propagation. If you had a long string tied to an object and you stand at the very end of the string and move it up and down in a vertical manner, such as the figure in the top, then the signal is vertically polarized. If you move the string horizontally from side to side, then that signal is horizontally polarized. And similarly, the antenna can receive either the horizontally or vertically polarized backscattered energy by applying specific filters. NISAR can receive both, so it can transmit and receive both. So there can be 4 combinations of both transmit and receive polarizations. HH, that means horizontally transmitted and horizontally received. VV, vertically transmitted and vertically received. HV, horizontally transmitted and vertically received. And VH, vertically transmitted and horizontally received. So NISAR's polarimetric capability is important because it allows the radar to do more than just see the surface. It helps understand the orientation of the structures on the surface. And NISAR has different acquisition modes. Depending on the acquisition mode, either all polarizations are collected or just a subset of these polarizations. So we discussed two important radar parameters in the context of NISAR, that's wavelength and polarization. And the radar backscatter is in part driven by these two characteristics. The reflection of the signal is also driven by the characteristics of the surface. So this is super important. Radar is sensitive to two things. One is structure and the other one is moisture. So let's start with structure. In general, there are three parameters related to structure. That's density, size relative to wavelength, and size and orientation. So we discussed size relative to wavelength. Here we have an example of an Austrian pine, and that wavelength will, or that wave, that signal will interact with components in the surface that are approximately the size of the wave, right? So in this example, at X-band, which is about 3 centimeters, we're primarily seeing the needles in the Austrian pine at the top of the canopy, and with L-band, we're seeing more of the longer branches. So L-band for NISAR 24 centimeters, we're looking at the longer branches, the trunk, and with P-band, even the longer structures that are more similar to the wavelength at P-band. Also, the longer the wavelength, the greater the penetration through the medium. Then there's density, and that signal will penetrate through the forest canopy all the way down, depending on how dense your vegetation is. And there are many different studies that have looked at the saturation point in terms of the above ground biomass, tons per hectare. And this value differs, that where that saturation point is, it differs between different types of forests, tropical forests and boreal forests. But the signal will definitely saturate at a larger tonnage per hectare the longer the wavelength as opposed to the shorter wavelength. So at L-band is more suitable to look at dense forest, S-band forests that are less dense. And C-band tends to be a better sensor for agriculture. And then there's size and orientation. We discussed polarization. So polarization provides information on the orientation of the components on the ground. The other surface parameter is the dielectric constant, which is controlled by the amount of moisture in the surface. And radar backscatter is influenced by the amount of moisture in the vegetation and the soil and the snowpack. And the larger the water content in a medium, the less the penetration. So the magnitude of the radar backscatter is proportional to the dielectric constant of the surface. So for dry surfaces, it's on the order of 3 to 8, the dielectric constant. For liquid water, it's around 40 to 80. This is frequency dependent. So the amount of moisture in the soil or in the medium can greatly influence an increase in radar reflectivity. And so what you're seeing here on the right is an example of an L-band. This is a JRS-1 image time series near Fairbanks, Alaska, in a place called Bonanza Creek. And you're seeing the transition of the land surface for the same area from mid-September through from mid-February to late September. And what I want you to note here is the change in reflectivity when things are frozen in this part of the world, in Alaska. Things are fully frozen in February, and then you've got a spring transition, and then you've got summer when things are thawed. So the radar backscatter increases when things go, in this case, from frozen, which is it has a very low dielectric, to spring thaw, when there's a large amount of water in the soil and things are thawed. Now let's focus on the science and applications that NISAR can address, as well as some early results. Summarizing some of the key characteristics of NISAR include its dual frequency radar system operating in both L and S band. The satellite provides near global coverage with the exception of the high latitude regions, especially the Arctic. NISAR has a 12-day exact repeat cycle. However, it requires 2 observations within each cycle, one in ascending orbit and the other one in descending orbit. The spatial resolution of the data varies between 3 and 10 meters depending on the acquisition mode. The mission has a baseline duration of 3 years for L-band and 5 years for S-band, and all data are or will be freely and openly available. L-band data is distributed through the Alaska Satellite Facility Distributed Active Archive Center, also known as the ASF DAC, while the S-band data, along with some L-band data products, will be available through ISRO's Boonity platform. Now, given these capabilities, NISAR will support a wide range of science and application areas, including solid earth processes, ecosystems, the cryosphere, soil moisture, and applied remote sensing applications. The mission has key science objectives organized into 3 main areas. The first is the cryosphere, which focuses on the dynamics of Earth's sea ice and major ice sheets in Greenland and Antarctica, as well as glaciers. And this includes examining how these components contribute to sea level rise. The second is ecosystems, and this includes understanding the dynamics of carbon storage, landscape disturbance, wetland inundation dynamics, and agricultural systems. And it also provides a unique capability for estimating standing biomass and carbon stocks as they are distributed across the globe. The third is solid earth science, which focuses on processes such as earthquakes, plate tectonics, volcanic activity, and landslides, as well as related geohazards. And together, these 3 science domains are supported by dedicated science teams working across each area. In addition, the mission includes important applications objectives, and these include understanding societal impacts related to hazards, water dynamics, ecosystem restoration and degradation, as well as their links to broader societal needs. In agriculture, the mission supports food security applications by monitoring land use and crop activity, distinguishing between actively managed farmland, fallow areas, and crops intended for food production, as well as monitoring soil moisture. There's also an urgent response capability enabling rapid tasking for events such as oil spills, storms, earthquakes, and other natural hazards. And this allows the mission to acquire additional targeted observations and deliver data quickly to the user community, which is a particularly powerful aspect of the mission. And in particular for India, there is a very strong focus on coastal processes. This is an example of a complete 12-day cycle at L-band HH polarization. The data used to create this mosaic have not yet been fully calibrated, and as a result, some radio frequency interference is present in certain areas. However, this example serves as an illustration of NISAR's L-band coverage over land and ice. And it also provides a sense of the mission's ability to generate and manage a very large data volume on the order of approximately 1,300 frames per day, about 16,000 frames per 12-day cycle, and roughly 500,000 frames per year. This is a preliminary result of biomass with NISAR, and I mentioned previously that biomass dynamics are extremely important, and these results illustrate the relationship between polarized backscatter and biomass. This information can be used at the calibration and validation sites shown on the left to generate biomass maps as illustrated on the right. And as you can see, the system is able to estimate biomass across a wide range of conditions, including very high biomass levels exceeding 200 metric tons per hectare. And this capability is also important for improving climate cycle modeling. This is an example of wetland inundation. So this is a false color composite, and what you're seeing here in purple are inundated areas, vegetated inundated areas. So whatever is dark, that's river, that's open water, and all of the pink areas are inundated vegetation. And this inundated vegetation is something you would not see with optical data. Another example is this striking image related to ice sheets. And on the left, you can see a series of ice streams flowing across Antarctica. The feature highlighted in the red box is shown in greater detail on the right. And this area corresponds to a topographic mound beneath the ice sheet. And as ice flows through the region, it's diverted around the obstruction, which causes deformation and fracturing of the ice. And this process produces extensive crevasse fields, sometimes referred to as hairline crevasses, although they are far from small, spanning, as you can see in the scale here, several kilometers. And so these features are clearly visible in the radar imagery in NISAR, and they arise in part because the radar signal penetrates to some depth into the ice, and it scatters from internal and surface structures and returns to the sensor. So measurements like these are used to study ice dynamics, including ice flow behavior and its interactions with both oceanic and atmospheric processes. So here's another ice-related example where we directly measure velocity using interferometric techniques. On the left is a radar image of an ice field, and you can see some areas appear slightly defocused, and that's due to signal penetration effects. But the rougher regions clearly reveal the location of the ice stream. And this example is from Jakobshavn Glacier in Greenland. On the right, you can see a time series that's been generated by combining one image with another acquired 12 days later and forming an interferometric pair. So from this, we can estimate ice surface displacement and derive velocity. In this case, the NISAR data have also been combined with Sentinel-1 data from a different viewing geometry to generate a full velocity vector field that shows ice motion of approximately 3 kilometers per year in this region. That's a very fast-flowing ice. Tracking the variability of this dynamic behavior over time is one of the primary objectives of NISAR. The mission enables seasonal scale monitoring, whereas other systems have required up to a decade to produce a single velocity map. So this represents a significant advance in our ability to understand ice dynamics and their relationship to climate. So here's a solid Earth example. Another important application of interferometry is tracking earthquakes, volcanic activity, and other forms of surface deformation to better understand processes that are these dynamic processes occurring within the Earth's crust. And this example shows a volcanic event in Ethiopia, captured using a time series. So in the lower right, you can see the difference between two images acquired November 10 and 22nd of last year. And the subtle color variations reveal surface deformation. So these are areas of subsidence and uplift indicating subsurface magma movements. And so in some areas, the magma chambers are losing material, while in other areas, they're being recharged and may be approaching eruption. So in the subsequent 12-day interval, the data showed that an eruption did in fact occur. The magma that had accumulated in the system was released and that dike effectively closed. So the colored fringes that you see are also known as interferometric fringes, and they represent the magnitude of ground displacement. And in this case, it's on the order of 0.5 meter to 1 meter. And remarkably, we're able to measure this level of deformation from space with centimeter scale precision using NISAR. And this capability is repeated every 12 days over the lifetime of the mission, providing, as you can imagine, a very powerful tool for monitoring these dynamic geophysical processes in near real time. Soil moisture is another key variable that is being measured by NISAR. It's critically important for things like agriculture, hydrological models of evapotranspiration, drought monitoring, weather forecasting, and related applications. And here you can see an example of the soil moisture product at field scale. Previous satellite-based soil moisture measurements have generally been at relatively coarse spatial resolutions on the order of 9 kilometers or more. In contrast, these observations that are approximately 200-meter spatial resolution. And this represents field scale variability in soil moisture, which is highly valuable for the agricultural community. And of course, there are a number of applications that NISAR can address. Here are some examples, and you can access these white papers through the link on this slide. Now let's focus on the science and applications that NISAR can address, as well as some early results. So this figure illustrates NISAR's observation plan, which defines how the satellite acquires radar data around the globe. So rather than using a single imaging mode everywhere, the mission employs multiple radar acquisition modes optimized for different science objectives. And these modes also provide different spatial resolutions and polarizations, allowing NISAR to balance detailed observations with efficient global coverage. L-band observations provide near global coverage of Earth's land surface, including islands, as well as the major ice sheets and sea ice. In contrast, the S-band acquisition strategy is more targeted. ISRO's primary focus is on the Indian subcontinent, other regions of South Asia and Antarctica, so S-band data are not collected globally, just over targeted, over specific areas. And in addition to those areas, S-band observations are also acquired over a global network of calibration and validation sites. And these locations provide then unique opportunities to combine L-band and S-band observations, helping scientists better understand the complementary information provided by the two frequencies and the benefits of using dual frequency radar measurements. The observation plan is reviewed and updated approximately every 6 months based on science team member recommendations, available mission resources, and other programmatic considerations to ensure that the mission continues to meet its evolving science objectives. These are the different NISAR data product levels, and like most NASA Earth observing missions, NISAR organizes its data into a series of processing levels. So level 0 consists of the raw telemetry and signal data. Level 1, data products have undergone some initial processing and calibration, but remain in the radar's native, or in the satellite's native geometry, also known as range Doppler, rather than geographic coordinates. Level 2 products are geocoded, meaning they have been projected into geographic coordinates, latitude and longitude, making them easier to integrate with other geospatial data sets. These products include calibrated radar backscatter, interferometric phase, unwrapped interferograms, and other geophysical measurements. So these are considered analysis ready. Then level 3 products are the higher level geocoded derived science products expressed in physical units. So the only global level 3 product generated by NISAR is soil moisture. There are algorithms, they're known as ATBDs, which stands for Algorithm Theoretical Basis Document. These are algorithms that have been generated by the different disciplines, and they have been validated over calibration validation sites. And so these algorithms are focused on generating biomass, vegetation disturbance, wetlands inundation, crop area, surface deformation, damage proxy, ice sheet glacier velocity, and sea ice velocity. And all of these ATBDs are openly available. So NISAR data products consist of backscatter and phase, as well as interferograms that contain information on surface deformation, as well as coherence, which is the stability of the surface on the order of centimeters. There are also pixel offset products generated using the backscatter data, and these identify large shifts in the surface on the order of meters. And finally, there's the soil moisture product, which is a 200-meter spatial resolution. You'll notice that many of these data products are derived only over cryosphere regions, and the rest is global or near global. Now, if you're new to radar and you're doing, for example, ecosystem type studies, land cover classification, or you're looking at fire burn scars, or you're looking at agricultural growth through time, you'll want to use the GCOV data product. So that is the geocoded covariance matrix. So that's basically the backscatter data at multiple polarizations, and that data set has been radiometrically and terrain corrected, so it's analysis ready. If you're new to NISAR, then you'll want to use the GUNW, which is the geocoded unwrapped, and it contains also the wrapped interferogram. So these are both level 2 data products that are produced globally. NISAR data status. In February of 2026, a large number of pre-calibrated global data products were made available, and this release included over 100,000 level 1 to 3 products, totaling over 500 terabytes of science data. In July of 2026, the calibrated forward processing data will be released. So after the calibration phase concludes and planned software improvements are completed, the NISAR project will begin forward processing of the newly acquired data. So forward processing is targeted to begin in sometime in July of 2026, so sometime during this month. The fully calibrated level 0 to 3 products will be continuously generated from all data acquired from the start of forward processing into the future, and new data will be continuously published to ASF and made publicly available. Level 1 to 3 products will have a nominal latency of 36 to 72 hours from data acquisition to availability. The Q3 to 4, so there's a calibrated back processing. So after the start of the forward processing, the NISAR project will produce calibrated level 0 to 3 products from the backlog of all data collected from September 23rd, 2025 through the start of the forward processing in July 2026. And this processing will be completed sometime before the end of calendar year 2026. So the Alaska Satellite Facility is the data archive center for the L-band data, and ISRO's Boonity platform is the data archive center for the S-band data as well as for overlapping L-band data. If you'd like to learn more, you can scan the QR code on this slide. Data can be downloaded through ASF's web-based graphical user interface, or it can be accessed programmatically using an API, making it easy to incorporate NISAR data into automated workflows. All NISAR data are freely and openly available and are hosted in the Amazon Web Services cloud, providing fast and scalable access for users around the world. Now I'll show you a short demo on how to use the GCOV product to visualize flooding between two acquisitions, one during a high flood period and another one during the low flood period. All right, so the first thing we're going to do is we are going to go to the Alaska Satellite Facility ASF Vertex tool. So go to Google and do a search on your web browser, and we'll select here our first result. Now, this is the Vertex platform, and the default is Sentinel-1. What we want is NISAR data. Note that this is uncalibrated data. So in February of 2026, there was a release of over 100,000 NISAR data products. These are all uncalibrated. So today we are working with the uncalibrated data. There are issues with the data, and I'll show you what some of those are. The plan, as mentioned, is that sometime in July of 2026, late July 2026, there will be a release of the calibrated data, NISAR data. So let's just select NISAR. And again, there are over 100,000 data products available. Let's do a specific search. This example is a flood visualization example. So let's just look at Colombia, because I know there was a period of high flood and low flood there. And let's select specifically the GCOV product. So that is the radiometrically terrain corrected backscatter data in different polarizations. In the case of overland, at least in this region that I specified, it's just HH and HV primarily. So let's do this. So I'm going to draw my area of interest, and under filters, I'm going to select the GCOV data product, and I will do search. And so there are 236 NISAR files over my area of interest. So let's just zoom in. And I know I've already located an area where there's interesting flooding. So it's this frame right here. And that frame is this one. Whichever frame I select, you can see a quick browse image right here. But we're specifically interested in this one. So let's just click on that browse image, and it'll open a separate window where you can actually take a closer look at that browse image. So I'm seeing a lot of flooding here along the river. This is double bounce, all of these purple areas. As mentioned, these are uncalibrated data. So what you see up here, this bright green area here, that's radio frequency interference. So that's noise, that's RFI. And that is going to be resolved in the release of calibrated data that we will be doing later in July 2026. All right, so this is an interesting image because of the flooding. And so one thing I can say is I want to see images more like this. So I want to see the time series of images over my specific area of interest. Okay, and so these are the images, the exact area. And let's take a look. So the nice thing about Vertex is you can actually take a look at these browse images, take a quick look. And what I'm seeing here, what I'm most interested in is the flooding, the bright purple areas along the river. That's inundated vegetation. Okay, so I'm going to select, and you see this one has a lot of that inundated vegetation here along the river, while this one doesn't. And neither does this one. So I'm just going to select October 29th and December 4th. And in order to download the data, you go to the HDF5 file. So there are a series of files here. This is the actual data file, and you download the file. It's pretty large, or you can add it to your carts. So I can add these two images to my cart and download both of them at the same time, or I can individually download it. So I've downloaded the images already, and let's just go to QGIS and take a look at the images and create an RGB. Okay, so I have the latest version of QGIS 3.44, the stable version. And what I do is I go to layer, add raster layer, and then I select the file of interest. So I need to go here. I actually downloaded 3 different dates, but we're going to use 2 dates for this example. So we're going to use the October 29th and December 4th. You can see it in the name right here, 2025 1204. And this one is 2025 1029. Okay. Now, let's start with the 1029. That's the October. That's where we saw the flooding. So let's call that the high flood image. And we'll open it. Now, what happens is QGIS does not have a reader to recognize this version of HDF5 that NISAR is using. That's still in development. We're developing the GDAL reader still. So what you need to do in QGIS is you need to trick it so it thinks it's a netcdf file. And the way you do that is you go to the front, to the very beginning, and just type netcdf : okay? The other way to do this is just to change the extension in the name of the file. Instead of HDF at the end, just change it to .nc. So there are two ways, either specifying that it's a netcdf in the path at the beginning, or changing the extension from HDF to .nc. So let's just go this way and we'll say add. And these are HDF5 files, so they have a bunch of different files within it. And the one that we want is this one, the frequency A. There are two polarizations, HH and HV. In this case, we're just going to work with the HH data, frequency A. So that's a 10 meter spatial resolution. And we'll say add layer, close. So this is the file. And it's always good to view it. And what we will do is, so it's loading right now since it's a very heavy file. Okay. And this is, you see that it looks very dark or very bright. So that has to do with how this QGIS is doing the histogram stretch to visualize the image. So what we do is you double click on the file name, you go to symbology, and just set the max min. So this is a cumulative count cut based on percentile, and just select that. And that's our image. Okay. So let's do the same thing. We'll open this is the October. Let's open the December file. Same way, add raster layer. And here we'll just select these are very long file names, but this is the December 4th. We'll open it. Again, we add netcdf at the beginning. And we select the frequency A HH band, okay? And we say add layer. Okay, so here we have our two images. It takes a little while to load. And it's always really good practice to look at your images and just make sure that everything looks okay. So again, we'll do the cumulative count cut. Okay. So the next thing we do is we will subset these images. And in order to do that, you go to Processing Toolbox. Oops. Processing Toolbox and clip raster by extent. So I recently used that, but you can go to raster extraction and select clipped raster by extent. Okay. And so we want to clip, let's see. This is the October image. So let's start with that. And let's say that the extent that we want to clip is what we draw. We'll draw the extent. So I'm going to go here, and this area, this is where the flooding occurs along the river here. So we'll clip this area and we'll say run. Great. Close. We will rename. So you double click on the file name, the clipped extent, and you right click and you select the rename the layer. Okay. So this is October 29, 2025 HH clipped. Okay. Now we want to do the same thing for the next image. So again, we say clip raster by extent. And we want to clip the December file. So it's this one. You can see at the date here. And then clipping extent, we want to clip it according to the same extent from the first image. So we say calculate from layer and select the image that we just clipped. So it'll clip according to the extent of that extent. And we say run. Okay. So let's just visualize this. First of all, the October 29. Say, opera. Symbology, min-max, cumulative concut. Okay, that's the October 29th. And then let's visualize let's rename this one. This is December 4th. So we'll say December 4, 2025 HH clipped. And we will visualize it again. There. Okay, so that's my clipped image. So we have two clipped images from different dates. The next thing we want to do is we want to convert these. These are digital numbers. We want to convert them to decibels. And again, these images, the terrain has been corrected. And they're radiometrically corrected. So when we convert them to decibels, they're actually in gamma naught. Sorry. So in order to convert them to decibels, you go to raster calculator, and we'll say we input the expression here, which is 10 times log 10, and in parentheses, you then specify the file that you want to convert to dB. So we'll select this one, and we need to close the parentheses. And the output layer, we want to say where we want to put this file and give it a name. So this is December 04, 2025 HH clipped, and we'll say it's dB. Okay. So we press OK. And this is our dB image. In this case, I'm just going to set the values for visualization. So usually the values go, say, from -25 to, let's say, -2, or let's say 0. Okay. And you can play around with that for a better visualization. So that's the December 25. We'll do the same thing with the October file. So we'll say this 10 times log 10, and the October 29 is the one that we want to convert to dB. So you double click and it fills it down here. And then the output layer, again, you specify where and you specify the name. And in this case, it's October 29, 2025, HH clipped DB. Okay. And we say, okay. Again, we will stretch it from -25 to 0. And all of these bright areas that you're seeing, again, that's inundated vegetation. So one thing we want to do is let's just create an RGB. And in order to do that, we will build, we need to build a virtual raster because these images are independent. So let's go ahead and build a virtual raster. And we say, place each input file into a separate band. So let's just select our input bands. So we'll select December 4 and the clipped DB, and then we'll select October 29, the clipped DB. Okay, so we have 2 bands. And what we want to do now is visualize that as an RGB. So you double click, you select multi-band color, band 1, and let's just say -18 in all of them, min. So that's how we're stretching the visualization. And max, let's just say it's 1. So in the red band, we have band 1. In the green band, we have band 2. And in the blue band, we'll have band 1. Okay. So what we're seeing here is that all of the green areas, those are areas where whatever is in the green channel has a higher value. So what the green channel has the high flood, the inundated vegetation. So all of these green areas that you're seeing, all of that is flooded vegetation that's there in October, on the October 29 scene, and not in the December 4th scene. So this is just a simple RGB with just 2 images. So a couple of important points to remember. NISAR is designed to monitor continuous Earth surface changes on the order of centimeter to meter scale globally. It has a capability to image the Earth's surface day and night and through almost all weather or cloud conditions. The key focus processes include tectonic deformation, ice sheet movement, ecosystem change, and agricultural monitoring. NISAR has an L-band and an S-band radar, so L-band 24 centimeters, S-band 9.4 centimeters. The satellite has an exact 12-day repeat cycle. However, there are 2 observations within every 12 days. One is in the ascending orbit, the other one is in descending orbit. It uses a 240-kilometer imaging swath using the SweepSAR technique, and the spatial resolutions vary between 3 and 30 meters depending on the radar mode. NISAR has a repeat pass interferometric capability, and that allows for measurements of surface deformation on the order of centimeters. The polarization acquisitions vary depending on acquisition mode, and the core science disciplines cover cryosphere, ecosystems, and solid Earth. NISAR can also address different applications and support disaster and hazard management. NISAR products are openly and freely available. The L-band data is available through the ASF DAC. That's global data. The S-band data, along with coincident L-band data, are available through ISRO's Boonity platform. The S-band acquisitions are over India and targeted locations around the world. Data processing levels span from level 0, which is the raw data, to level 3, which are the geocoded derived products, with soil moisture being the only level 3 global product being generated. Level 1 and level 2 products contain information about amplitude, phase. There are interferometric products, there's coherence, and there are pixel offsets. The level 1 products are in the satellite native coordinates, range Doppler, and the level 2 products are geocoded and analysis ready. The data are in HDF5 format. For those interested in doing ecosystem type studies, probably the best data sets are the GCOVE and the GSLC data. In terms of data status, in July, in this month, 2026, the fully calibrated forward process data will be released with a data availability latency of 36 to 72 hours. And then in late 2026, the back processing of the archived global historical data will be released. So that will be the data acquired by NISAR spanning from September 2025 through the beginning of this forward processed data release. And looking ahead to session 2, NISAR data access and tools. You will learn how to identify where to access NISAR data, recognize the data format and tools for reading the data, and apply tools for visualizing and analyzing NISAR data. Homework and certificates. There is one homework assignment associated with this training. It opens on July 16th and the due date is August 6th. You can access the homework through the training webpage. A certificate of completion will be awarded to those participants that attend all 3 live webinars and complete the homework assignment by the deadline. You'll receive a certificate via email approximately 2 months after completion of the course. If you have any questions, feel free to contact me via my email posted here. And here are 2 great resources for those that want to take a deeper dive into NISAR. One is the NISAR handbook, the second version of it. And the other one is the NISAR data user guide by the Alaska Satellite Facility. And the QR codes, the one on top is for the handbook, the one on the bottom is for the user guide. That concludes the first session of this training. Thank you very much to everyone participating. Thank you for all the questions. We are now ready to start the Q&A session. Great. So there have been a lot of really great questions coming in, a lot of conversation on the chat. We have been compiling your questions on a Google Doc, and we will be sharing that in just a few moments, and we will start answering your questions. I don't think we'll have enough time to get to all of your questions, but we will be responding to all of the questions on the Google Doc, and we will be posting this document on the webpage. So let's start with question number 1. Do NASA and ISRO plan to launch other NISAR satellites in the future to have NISAR constellation increase the temporal resolution of the acquisitions? That would be absolutely fantastic. I am not aware of. However, I will consult if there are any sort of conversations, and I will update this, but not that I'm aware of. Question number 2. If we're interested only on structure, should we try to obtain imagery during dry periods of the year? And the response to that is that if you are studying vegetation structure, you should really try to acquire imagery during both the dry and wet seasons, because the structural characteristics of the vegetation can differ significantly between these 2 seasons. So I wouldn't just try to use imagery from the dry season. Okay, question number 3. How deep in the soil can SAR or INSAR penetrate? This is totally dependent on the frequency, the polarization, as well as the soil wetness. So again, the longer the wavelength, the greater the penetration. So L band will penetrate further into the soil than S band. And the wetter the soil, the less the penetration. But the NISAR soil moisture product that I discuss represents the average volumetric soil moisture of the upper 5 centimeters of the soil. Question number 4, you said NISAR can penetrate through soil. Can it be used to detect and study the heavy metal contamination in the soil? So this is an interesting question. It likely cannot be used to study heavy metals in the soil, because again, a radar is not sensitive to the chemical properties of the surface, but rather to structure and to moisture. Now, if there's say a large area that is contaminated with heavy metals, where the dielectric is different, right? So the wetness is different because of those heavy metals, then you might be able to see differences. You can't correlate it necessarily why one area is wetter or drier than another area, but you would be able to see those differences if it's large enough, right? So indirectly, there might be some correlations. Question number 5, can interferometry be used to study vegetation changes? How can NISAR contribute to mapping deforestation in tropical forests? So just for your information, we will be diving deep into that interferometric component of NISAR in session 3. So my colleague from JPL, Eric Fueling, will be leading that session. He'll be providing a brief background on INSAR and discussing the NISAR interferometric products and where they work well and where they don't, and the type of corrections that you need to do. However, to answer your question here, the best NISAR product to study vegetation changes is the backscatter product. So that's the Amplitude, and that's the GCOV, the GCOV product, the level 2 GCOV at different polarizations. So with that, you remember when I was discussing the fundamentals of SAR, how you have the scattering mechanisms, and within a forest, the signal bounces from many different components. So the backscatter signal can detect biomass. You can use that for doing estimates, not detect, but you can do estimates because you need an algorithm to do estimates of biomass. And you can also look at forest disturbance, as well as wetland inundation, agricultural growth through time. So to do those, so for ecosystem type studies, the best product is the GCOV product. Okay, and deforestation is pretty straightforward in the sense that the change in the signal, in the backscatter signal, is pretty significant from an area where you have forest, where you have high backscatter, relatively high backscatter, to an area where you do not have forest, where you have very low backscatter. Okay. The next question. Question number 6. Can NISAR effectively distinguish between open water, emergent vegetation, and invasive aquatic vegetation in complex wetland ecosystems? So L-band can very well distinguish open water because smooth water surfaces produce very low backscatter. Obviously, sometimes there's some sources of confusion. So in the open water, for example, if you've got wind, it's going to look a little rougher. It's not going to look as dark. So sometimes you have some sources of confusion, but L and S band can very well, C band can very well distinguish calm open water. Now, L band is less effective at detecting low emergent vegetation, especially if that vegetation is sparse or has a very simple structure. And by that, I mean, if it's emergent and it's just a couple of centimeters, remember how I said that the signal interaction depends on the size of the component. So L band is about 24 centimeters. And if that emergent vegetation is just a couple of centimeters, 4 or 5 centimeters, that it's going to look like an open water, It's not going to detect it. But S band would be better suited for detecting that emergent vegetation, as well as C band. And then this person also asked about invasive aquatic vegetation. Hard to respond to that. I'm not entirely sure. If it's underwater, obviously we can't. The signal is not penetrating through the water. But if it's above the water and that invasive vegetation has enough density and is structurally different than the surrounding vegetation, then you might be able to detect it with radar. All right, the next question, number 7. I've been studying the principles of weather radar, specifically how we manage signal clutter. Given that NISAR is an L and S band system, how do the clutter removal and ground processing algorithms in NISAR compare to the techniques used in traditional Doppler weather radar networks like Opera? Okay, so I'll elaborate on this response. I need to consult with some of my colleagues. However, weather radars are different than NISAR. Weather radars operate at much smaller wavelengths because at that point you're looking at the interaction of the radar signal with water droplets. So you need much smaller wavelengths. And radar networks like Opera. So Opera is a platform. It's an observational products for end users. So these are products that are being derived from remote sensing data. And these Opera products, and the next session, number 2, will discuss some of the Opera products. They don't use the weather radar data. They use Sentinel-1 data, they use optical data, and they'll be using NISAR data to generate these end user products, which are related to surface water extent, surface disturbance, displacement, vertical land motion. Okay, the next question. How will NISAR's dual frequency L and S band SAR observations improve Earth monitoring compared to existing missions? And what applications do you expect to benefit the most? I think there are many different things. L band sees deeper and larger structures. S band sees shallower and finer structures. So combining them will provide a more thorough characterization of an ecosystem. So L-band will works well in areas where you have dense forest. S-band works better in areas where you have less dense forest. So when you combine these unique capabilities or information content from these different bands, then you can have a more thorough characterization of your ecosystem. And what applications do you expect? I think that's all. It's also up to the end user, like what they want to explore in terms of the complementary use of L and S band and even C band. There's Sentinel-1 data. So how can you exploit the unique information content in each of these different bands to come up with more thorough or generate more thorough either land cover maps or just different sorts of products. I think this is super exciting, this era of like multi-frequency SAR data. All right, we have a short question, number 9. Swath range, pixel spacing, and resolution per mode. Wow. Okay, so the swath is 240 kilometers for most areas. Some areas are half swath. The pixel spacing that varies between 3 and 10 meters for the lower level products, and that totally depends on the acquisition mode. Number 10, I would like to ask how NISAR has proved to be better in flood mapping and climate change analysis than the optical remote sensing satellites, for example, Landsat. Okay, so NISAR, so we haven't yet proved to be better. It will be better, because we're still working on the calibrated data. So the data that we have generated and released is pre-calibrated. So we really haven't started that period of like really rigorous science analysis with calibrated data by the community. However, we expect this to be huge, the data to be huge in terms of supporting flood mapping because of that unique capability that NISAR has and radar and L-band in penetrating through the vegetation canopy and detecting standing water underneath the vegetation. And this is something that just simply cannot be done with optical data because optical is really just seeing the top of the canopy. And in areas where you have very dense vegetation, like in tropical forests, you're not getting a sense of the extent of inundated vegetation. So, and given NISAR's relatively high spatial resolution and the temporal repeats, exact temporal repeat every 12 days, but really 2 observations within those 12 days, so every 6 days, I think this is going to be game changing, really, for the study of wetland ecosystems, looking at wetland inundation dynamics and extent. All right, question number 11. Can NISAR data be downscaled with multi-input neural networks? Yeah, that's a great question. I don't have an answer to that. It might be. I think there are many, many, many things that are worth exploring with the NISAR data, and this is one definitely worth investigating to see what sort of results you can come up with. Okay, so please, I didn't understand the left side looking and the consequences on the North Pole. So because of the look geometry and the orbit, so it's in it's a sun synchronous polar orbit. The North Pole has larger gaps with just the way the orbit and the fact that it's left looking. And so with NISAR, we've really prioritized the Antarctica observations in Antarctica, which in the past, I think most radar sensors, at least openly available radar data out there, they're right looking. So they've prioritized observations over the Arctic, but less so over Antarctica. In this case, it's the other way around. So observations from other radar sensors fill in the Arctic, while NISAR really fills that gap in Antarctica and the South Pole. All right, the next question. When will NISAR data be available in Google Earth Engine? That's a really good question. I get that question a lot. And the answer is that we're not sure if it's going to be available in Google Earth Engine. However, we are discussing this possibility. And we hope in sometime in the future to have an update on whether that will be possible or not. Question number 14. Which DM is used for the radiometric correction? So the DM that's being used is the Copernicus Glow 30 meter DM. Question number 15. How can we use the dual pole, HH and HV, available globally to differentiate in specular double bounds and volume scattering phase during different crop growth stages? So that's a great question. I think there are different ways, right? So HV tends to be much more sensitive to the presence of vegetation than HH. And one thing you can do is you can look at time series of HV to look at crop growth. Another, now, if you want to look at the dominant scattering mechanisms, so if you want to understand whether within a pixel the dominant scattering mechanism is double bounce or surface scattering or specular scattering, you can do quasi-polarimetric decompositions. And this is a great point. One of the things I do want to do as we move forward into more intermediate type NISAR trainings is to have some tutorials showing how to do these decompositions and what sort of algorithms are out there. Okay, question number 16. This is a great question. How accurately can NISAR data generate a DM in a mountainous region? So one thing to clarify is that NISAR has this interferometric capability. It's a repeat pass interferometry. And so with repeat pass interferometry, we're within 100 meters of the the same point. So we're very close. We're always, whenever we have that exact repeat, we're very close, within 100 meters from the last exact acquisition. And so with repeat pass interferometry, this is much, much more suitable for measuring small changes in the surface. These are changes on the order of centimeters, but not suitable for generating a DM. You'll have errors on the order of many, many, many meters. So yeah, this is just to look at small changes in the surface, the type of interferometry that NISAR can do. And this is something that my colleague Eric Fielding will discuss further in session 3. Okay, question number 17. How can the polarizations inform on the orientation of an object? So it's, the best way to understand the orientation is to do an RGB. So if you have two polarizations, do a false color composite where you do HH in the red channel, HV in the green channel, and then HH in the blue channel. Just to start out with, just something very simple. And that way you can understand the unique information content in the in each polarization. So things that are brighter in HH, that means you have you have horizontal component there than in the VV, say, for example, if you had VV. So yeah, the best way is just to do an RGB of your different polarizations. Is there documentation? Question 18, is there documentation for the different applications? Yeah, there is, and I'll share a link here, but there was that one slide I showed of the different applications that NISAR can address, and there are white papers associated with each of those, and they're very informative and interesting, and they're very short, but they explain the capability of NISAR for addressing these different applications. Question number 19, how current is the current observation plan, or rather how far into the future is it applicable for? And might the areas of priority acquisitions like the US Midwest change in the next year? So
So that's another great question. I believe, as mentioned, this acquisition plan is going to be revised every 6 years, depending on the needs of the science team, and the community, the science, the science to address the science objectives. And I'll update when it's going to be revised again. I believe it's later, yeah, later this year. But there might be, um, if there are priority areas, that new priority areas identified, say in the US Midwest, where maybe four polarizations would be of great benefit, then that would be something definitely to consider the next time it's being updated. Question number 20, can we analyze images of first pass and second pass jointly? So I think this question refers to, can we analyze descending and images from descending and ascending orbits? And that's really good. That's a really good question. So the viewing geometry is slightly different between ascending and descending, because we're looking toward the side. And so if you have a mountainous region, you should never combine ascending and descending, at least, with the backscatter data. If your area is flat, then it should be okay. I personally do not like to combine ascending and descending. I deal with them separately. I'll generate a product with, one stack or the other, and then maybe compare or combine once the product is generated. All right, which band is good for soil moisture? So this is an interesting one, and part of the plans for ARSET is to have a NISAR training on the use of the soil moisture data product. So there are actually 3 different algorithms as part of the soil moisture product. And I think these algorithms are using different polarizations or a combination of the polarizations, but the best one will be HH. HV is more sensitive to the presence of vegetation and will have less penetration through the soil. So HH will have the greatest penetration through the soil, I think, followed by VV. Okay, the next question. All right, question 22. Considering NISAR's dual frequency capability, how do we plan to combine its deep penetrating L-band data with canopy-sensitive S-band data to solve a specific measurement challenge for research? That's a great question. As mentioned, the data is there. The only level 3 product that is being generated globally is soil moisture. So there's a lot for the community to explore. And these are certainly things to explore, is that complementary nature of these 2 different bands and how they can be used to solve something very specific to your research. All right, question number 23. How are slope parallel and slope perpendicular motion components projected into ascending NISAR line of sight displacement measurements for a west-facing landslide? For an east-facing slope with similar downslope and vertical motion, how would the line of sight displacement magnitude, sign, and sensitivity differ compared to the west-facing slope? Okay, so that's a great question. So in the ascending mode, the satellite is looking left So it's looking towards the west. Um, and so this is, so I will respond to this question in the document. But as mentioned, the third session we'll take a deep dive into the INSAR products, and specifically these sorts of questions that you're asking about, like related to the line of sight of the observation. What sort of movement are we actually looking at with the interferograms that are generated? Number 24, what are the most promising applications of NISAR data for atmospheric science, climate research, and natural hazard monitoring in the coming years? I think there are many. So atmospheric science, as mentioned, NISAR is not a sensor to do atmospheric science. However, when you have measurements like soil moisture, that can feed into evapotranspiration models, into weather models. And so I think, there's a lot of stuff or different sorts of research that the products that can be generated will support. Natural hazard monitoring, there's a whole area within applications that addresses disasters. And so looking at, for example, with the INSAR products, you can measure small changes in the land surface. So if you see an area, for example, landslides, if you're looking at an area where you're seeing small movements through time, that might be indicative of an area that might be at risk for a landslide, right? If it's in a sloped area. If you're seeing, for example, you can also detect floods, which is, as mentioned, it's ideal. So natural flooded ecosystems, but floods related to disasters. And usually you can do assessments of the extent of the flood. When these sorts of things happens, there's a lot of cloud cover. So it's very beneficial that we have a radar sensor that can see through clouds and provide those assessments. Obviously, those assessments can only be provided as long as there's an observation. But yeah, there are many, many natural hazard monitoring, looking at volcano movements around volcanoes, which might be indicative of volcanoes becoming active, movement around tectonic plates and faults, which might indicate areas where there's a higher likelihood of earthquakes. So there's a lot that NISAR can support. How does NISAR's question number 25? So I will answer that one separately in the Google Doc. Let's carry on to question number 26. Usually it says SMAP provides cubic meter over cubic meter, but here you show it as a percent. Are these comparable? This percentage represents the amount of soil moisture per volume. What is the maximum depth that NISAR can reach? Okay, so that's a great question. It is comparable. It's volumetric. So it is the volume of water within a volume of soil. And the maximum depth that NISAR can reach, as mentioned at the top, NISAR, the NISAR soil moisture kind of represents soil moisture in the top 5 centimeters. But, actually that's going to totally vary depending on many, 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 many different things, depending on the texture of the soil, depending on the amount of water. So basically, the wetter the soil, the less the penetration. But there have been studies from way back showing that L-band can penetrate soils, and this was a study like in the desert somewhere, where there was no vegetation and super dry soils. It showed that the L-band signal could penetrate through that dry soil on the order of 1.5 to 2 meters. So in the case of NISAR, again, it just represents the top 5 centimeters. All right. The next question, number 27. When you mention interferometry measurements combining NISAR and Sentinel-1 data, are you describing bistatic collections? No, this is not bistatic at all. This is a combination of NISAR data, which is more contemporaneous, measurements from pre-calibrated measurements since middle of September 2025. And the Sentinel-1 data in that example was used to go back in time. So for that historical context. Question: how is it possible to combine L and S bands if their resolutions are different? So, the S band products have the same, they're the same level products as L band. It doesn't matter if the resolutions are slightly different. You can interpolate or extrapolate one to the other. And you will be learning a little more about the S-band data and its characteristics and how to access it, even though ISRO has not yet made available the S-band data. There will be a short video about the Boonity platform. That's where you can access the S-band data through ISRO. And part of that will discuss the characteristics of the S-band data. Okay, question number 29. Does each level have different spatial resolutions? Yes, so the different levels have different spatial resolutions. And, within each level, there are different acquisition modes. So for example, level 2, you have acquisitions over ice and over land, and those acquisitions are at different spatial resolutions. Question number 30. What products are built off NISAR right now? Are there partnerships with hyperscalers like Google for Google's initiatives using AI to improve Earth, or other AI for good initiatives by others? So I will respond to this question in the document. But right now, as mentioned, and as was the plan for the mission, there's the different level products. That's what we're concentrating on. And the only level 3 global product is the soil moisture product. I think there are plans or discussions about developing other products, but I will respond to that in terms of what those plans are. Okay, so we are 3 minutes past the hour. Let me see how many more questions we have. Okay, so we have quite a bit more number of questions. I will respond to all of the questions. It will take me a little bit of time, so give me about a week to polish and respond to the questions, and this will be posted on the on the page for this training. So with that, I want to thank everyone really for all the enthusiasm and all of the great questions coming in. And remember that there are 2 more sessions, great sessions, data access will be session number 2. That will be next Thursday at the same time. And then session number 3 will be in 2 weeks, and that will be on NISAR. So wishing everyone a great day, great weekend, and until next week.